All right, so I'm going to pick up this discussion of the multiple regression introduction by going to step 4. We've gone through the first 3 steps in the part 1 video. Here what I want to do in the second one is pick up with step 4, and we're going to test the model, except now testing the model isn't as straightforward as it was before, because before we just had this piece here, right? We just had the simple linear regression piece. So testing the model was asking the question, is X1 a useful predictor of Y? And now we have all this other stuff. And so when we talk about testing the model, we really need to take a look at how we're going to do that. And so this is going to tie into our model building quite a bit. And I'm going to come back and talk about testing the model in a separate lecture, but I want to introduce the ideas now, and then we'll come back and talk specifically in that lecture how we do this in our software, and then ultimately how am I going to do this in my project. But we're going to have a 3-pronged approach. First, we're going to do an overall test, and we're going to ask with the overall test, and I'll stop it there. We never include beta naught in the testing, but we're going to test and see, does anything work? Are any of the terms, or any of the variables, or any of the model terms, anything we talk about in the model terms discussion, quadratics, interactions, qualitative, quantitative, do any of those ideas work? Are any of those useful predictors of Y? It's a yes/no question. If we say yes, the way we're going to test it, does anything work? The alternative is going to be no, nothing works. And so I should say, then let's turn that around. The test is going to be comparing, does anything work to does nothing work, but nothing is going to be the null. If we say nothing works, we're done. We're going to stop. If we say something works, we're not done. If I tell you something works, hopefully you're thinking about a question you have right now. If I say something, you're going to ask, well, what part? And so that's the overall test. That's going to get us off the starting point. We're going to say, does anything work? Hopefully we're going to say, yeah, something does. And now we're going to have to go and find it. And so there's a couple different ways of doing it. There's a partial test and an individual test. And the one you use depends upon the question you're asking. If you're asking about several pieces at the same time, so maybe you're going for this, maybe there's a couple terms here, beta 8 and beta 9 out there, and you want to see, does something there work? Whenever you're doing 2 or more pieces of the model, we're going to use what's called the best subset, sometimes referred to as a partial F test, but that's when you're testing 2 or more terms. And this one, individual, is when you have just a single term. So 2 or more is a partial, 1 term is an individual. If you have a model that just has, and let me come in here and do this, if you have a model that just has this term in it, okay, so think about it from this way. If I want to test that term, the individual test and the overall test would be exactly the same, because the one term is the entire model. And that's the situation we ran into in the simple linear regression. But in multiple regression, obviously, that's not the case, because we have more than one term, hence the term multiple. And so what I'm going to do in this video is talk about and walk you through the overall test. And so we'll take a look at it. Again, I'm going to come back in another lecture and talk about these tests in more detail. But for now, we're going to do what's called the overall or the global F test. Overall global F test. In that preceding page, the overall test is a global F. The partial test would be called a partial F, and the F is referring to the distribution that's used. And the individual test would be a T test. It might be worth writing down. So the overall test says, let's test to see if anything works. Think about this. When we were working with a simple linear regression, okay, and again, I'm underlining there in blue the simple linear model. That would be the only thing we'd consider. To see if X was a useful linear predictor of Y, the null hypothesis said beta 1 is equal to 0. By stating that, it's really saying X doesn't work. X is not a useful predictor of Y. And now I want to say not only X, and not only X1, I also want to say X2 and X3 and X4 and all the way up through XK. I want to say none of them work. And again, I'm writing this in the context of there being K different variables, but we can also talk about different terms. So we might have a linear representation of X1, and we'll put it in just the way you see it here as the beta 1 X1. But I also might have a beta that's multiplied by an X1 squared, which would be the curvilinear representation of x1. What we're going to say in the global F test is that none of it, all the betas that are attached to x's, whether they're variables, terms, however you want to say it, all of those betas, again, not beta naught, but every other beta is equal to 0, meaning all this stuff here needs to go home or go away. It doesn't work. The x's don't work. They're garbage, they're crap, get rid of them. Okay? It's not really what the hypothesis you want to go with, right? Because we're hoping that the x's, we're hoping that the data works. We're hoping that the size and the location predicts the price of a house. We're hoping the mileage and the model predicts the price of a car. We're hoping that the size and location predicts the rent of an apartment. Got everybody there somewhere, right? You're one of those data sets. We're hoping that the variables work, so we're hoping that we can reject H naught and claim this. At least one beta, at least one of these guys is not 0. In other words, at least one of the terms that is in my model is useful for predicting Y. We'll come back later and talk about how do we find what's useful. If we reject, what do we do next? Great question. It's called model building. We'll talk. Okay, we'll come back to that. The way that we do this test, it's just a test, folks. It's just a test hypothesis. There's a test statistic and a p-value. They're going to be found on the printout. I'll show you where in a little bit. You're going to need to interpret a p-value. You there yet? When p is low, what do? We reject the null hypothesis. When p is high, we fail to reject. What's that mean in the context of this particular test? If we reject H naught, there's sufficient evidence to indicate at least one beta is not equal to 0. Something in the model is useful for predicting Y. And you see in parentheses there with the giant exclamation point. Find it. Okay, that's our next step. Again, we're not going to go there in this video, but that's our next step. Find it. What is it? Is it x1? Is it x2? Is it curves? Is it lines? The heck does interaction mean? These are some great questions that we're going to get to. Just let's take it a step at a time here. We're going to do a global F test. If we fail to reject, there's insufficient evidence to indicate that any of the variables are useful. We cannot say that any of these terms work. We'd stop. We would stop, but not on your projects. When you're doing a multiple regression project for me, nobody's going to fail to reject the global F test. Because if you stop, you're not going to get to do all the fun things we're going to talk about over the next several lectures. And so this will be the only time all semester on the global F test on your project you can choose any alpha necessary to reject H naught. It's the only time I'll let you choose an alpha above 0.10. If you need to reject if you need to choose an alpha 0.85 to reject, go do it. Don't worry about it. I don't care. I want you to do the project. I want you to go through the process. All right, so that's the global F test. How does it play out in our little example? Well, let me show you the printout. There's the printout. This is where I added in both x1 and x2. The t-test, this is what we looked at. We were over in here, right? We were looking at these things in the simple linear regression, and we were going to these p-values. There's only one of them, but we were going here. That's not where we look. This is t-tests. The global F is right down here. That's where we get our information. And so the test hypothesis in our case, if our model, remember our model is E of Y is equal to beta naught plus beta 1 x1 plus beta 2 x2. There's only two betas. So we'd set it up this way. We'd say both those betas are 0, beta 1 and beta 2. Meaning x1 doesn't work and x2 doesn't work. Nothing works. That's what the null says. And it says it through the betas. That's how we communicate. That's how we talk about our variables or our model terms. We do it through the betas. All the betas are equal to 0, and the alternative says something works. At least one of those betas is not 0. We're not going to say they're both not 0 because we don't know that. We're just saying something works. We go to that printout, we get the test statistic, the p-value. The question I get a lot, do I ever have to do anything with this p-value? Nope. When you're looking at F's, and also chi-squareds, by the way, but when you're looking at F tests, the p-value never needs to be halved, doubled. You never have to manipulate it at all. The only time you have to be careful about the p-value is when you're doing T or Z tests. That's that one-tailed, two-tailed discussion we've had on a couple different occasions now. When you're doing F tests, you're looking at multiple relationships at the same time. You never change an F p-value. Never. You do interpret it, however. What are we going to say here? This is a serious reject. At alpha equal 0.01, 0.05, 0.10, whatever one you choose. Usually in quiz or exam settings, I choose alpha so that there's a right answer and several wrong answers. But on projects, you get to choose. We reject H naught. There's sufficient evidence to indicate that something in the model or that the model is a useful predictor of peak hour volume. Peak hour volume is what our Y value is. Now, at least one of the terms are useful. You can say it a bunch of different ways. Something works, folks. That's good news. In addition, and I didn't really point it out in the printout, but we want to interpret our R squared here and look at that interpretation. Right now is a really good check of how you're doing in simple linear regression, because if you were pretty good in simple linear regression, you could interpret R squared there. Chances are pretty good you got this one. 95.19% of the variation of the sample peak hour volumes around their mean, the Y bar variation, the 95% of the variation in the sample Y values around their mean can be explained. We used to talk by, it can be explained by the linear relationship with X. We got a more complicated relationship. And so we changed that last part by the regression model. It's the same interpretation. R squared talks about the percentage of the variation that we can explain. S talks about how accurately we can predict. It's the same kind of ideas that we saw. The global F-test, completely new. We haven't seen that before. It's interpreting a p-value though. So a lot of this stuff we've seen, and that was the point of the simple linear regression. Get your feet wet. Get in there and see pieces of it. Okay, so what this is saying is we have a model that works. Reject H naught. Something works. That's good news. Look at our R squared. That's really high. That's good news. Now let's use it. And so step 4, we test the model. We interpret an R squared value. Notice I didn't mention the coefficient of correlation, because when you're talking about multiple regression, you outgrow the correlation. R squared, yeah, it's still around. So we only have the test, the hypothesis, and then we go to the R squared, and now we go to estimating and predicting. You can see there's a whole lot of red here, right? Again, in another video, I'll show you how to get this printout and how we're going to work with it. But I want to point out a couple things. It asked me, what values of the X's do you want to work with? And there's actually a couple different ways of doing it within the statistics, and I'll show you how to do that again in another video. But I said if the peak, we're trying to predict peak hour. If the 24-hour volume is, what is that, 20,000 vehicles, and the I-35 yes, no is 0, I came up with a 95%. I could change that number, but I generally leave that. I came up with a 95% prediction interval. When I say I, I'm being generous there. Statistics did that for Y. And again, the fitted value is for E of Y. I want you to be able to interpret these confidence interval endpoints. Can you do it? First, I'll start on this side, right? We are 95% confident that part's easy. And look what I'm saying. The mean peak hour traffic for all non-I-35 roads, that's what the 0 represents, non-I-35 roads with a 24-hour volume of 20,000 vehicles. This part here, between here and here, is saying these are the values of X. These are the X's, is probably a better way of saying it. Remember in our simple linear regression, we predicted the price of an automobile that had 35,000 miles, or we predict the price of a house that has 2,500 square feet. We specified the value of X that we were working with. Now we have to specify the values of the X's. Depends what your model is how many X's are going to be there, but you got to state it. We are 95% confident that the mean peak hour traffic for all non-I-35 roads with 24-hour volume of 20,000 vehicles will fall between 1953.2 and 1964.1. What about this side here? Rather than the mean of all, what are we going to talk about? We're going to talk about the value of a single one. Same values of X, right? Same printout. We are 95% confident that the peak hour traffic for a single non-I-35 road with a 24-hour volume of 20,000 vehicles will fall between 1918.5 and 1998.9 cars. The wording here is a little weird. I agree. What's it going to sound like on your project? I'm 95% confident that the price of a Mustang that has 40,000 miles falls between two numbers. I'm 95% confident that the average of all Mustangs that have 40,000 miles falls between two different numbers. If you got the apartments or the homes, it's going to sound something like this. I'm 95% confident the price of a house, and because we're using location, we'd probably say the price of a house in Tampa Palms that has 2,000 square feet falls between here and there. I'm 95% confident the average price of all 2,000 square foot Tampa Palms homes falls between here and there. The average of all, the value of a single one. Since now we have a couple values of X to specify, don't we? And in one of the X's in your project is either going to be a model, a vehicle, or a location. The other one's going to be a quantitative term like mileage or size. And so we do our same kind of confidence interval interpretations. And that's step 5, estimating and predicting. Really, we're just expanding what we're doing. And that's the introduction. Now I want to go one step further, and I want to go back and this printout. These guys here I'll make mention of, specifically these guys, the predicted interval. And then I'm going to talk about some values on this printout as well. The R squared, the standard deviation, the p-value. I'm going to point out those 4 things. Think about the R squared, the standard deviation, the p-value here on the global F test, and then the prediction interval, because here's what I'm going to talk about, using the model in practice. That's what we want to do. We want to build these relationships, and then we want to actually use them. When can I do that? And really what I want to talk about for the next couple minutes are 2 different types of significance. The first is statistical significance. Is your model statistically useful? The easiest way to look at that is to look at the p-value. And I'm talking about the global F p-value now. Are your terms useful for predicting Y? If the answer to that question is yes, if it's statistically significant, you're going to have a very small p-value. And if you say no, your p-value is going to be high. And so we need a small p-value. We'd like a high R squared value. P-value is more important here. We'd like an R squared value that's high. How high? It's a tough question. I can't really give you a number and say, well, it's got to be. It doesn't have to be. That's what we'd like. We need a small p-value. Okay, that's the statistical side of the coin, but just as important is the practical side. We've seen examples. I think the first example I looked at, we had a statistically significant model, but when I wanted to predict the sales revenue, the interval was so wide as I would be laughed out of the room. It's like, that doesn't help. I can predict the average age of students in my class. It's somewhere between 16 and 60. Statistically, I might say this is significant. Practically, you say between 16 and 60, huh? That doesn't help. I'm going to predict the price of a house. Yeah, the price of that house should be anywhere between $100,000 and $600,000. Statistically, it's significant. Size, location matter, good variables. Practically, it's crap. There's a price of a car somewhere between $10,000 and $20,000. Really narrowed it down there, didn't I? Practically, it's got to work too. How do we figure out if it's practically useful? We look at the standard deviation, and we look at the prediction interval primarily. You can also talk about the confidence interval. But look at that prediction interval on your printout. Is that useful to anybody? Is that going to be accurate? Look at the standard deviation. If you can tell me, and this is an interesting example, listen here closely here. If you tell me you can predict it within $10,000, now when you say $10,000, that's $10,000 this way, that's $10,000 that way. If you're talking about the price of a $20,000 car, that ain't that good. If you're talking about the price of a luxury, maybe a historic or antique car that's multiple hundreds of thousands of dollars, maybe that's really good. If you tell me your standard deviation on the house price is 30,000, we estimate most of the prices are going to be within 30,000 times 2, 60,000. Start saying, gosh, if you have a $200,000 home and you go 60,000 above and 60,000 below, you're at 140 to 260. That's pretty wide. That's not all that great. But if you're talking about $1 million homes that you can predict within 60,000, now you're saying, that ain't bad. So sometimes it's relative. You got to take a look not only at those standard deviation values, but also look at the numbers you're trying to predict. And you got to make a judgment call. Is it subjective? Sometimes, yeah. Sometimes it's not. If I tell you I can predict the average age of class and it's somewhere between 16 and 60, if you say, oh, that's not too bad, you're wrong. That's terrible. That's horrible. If you're predicting the price of a house and you tell me it's between $100,000 and $400,000, I'm going to laugh you out of the building. Oh, it's online class. I'm going to laugh you out of the internet. I don't even know if I can do that, but I will. I'll try. And so you got to take a look at this. We need all these things. And here's what I'll say. Of all of these, this one is your least important. If you have a small p-value, if you have a low standard deviation and you have narrow prediction intervals, I don't really care what your R squared value is. Your model is working. If you say, well, my R squared is a little low, so I don't think I'm going to use it, that's a bad call. Typically, if you have a low R squared value, let's say it this way, if one of these other things is bad, you'll also have a low R squared value. And so that's the least important, but it should be on the list. And typically I say of these 4 things, this is like 7th in importance. And you're like, that doesn't make sense. I'm trying to make a point. But those are the things you're going to look at, because I'm going to ask you a question on your multiple regression project. I'm going to ask, would you use this model in practice? And if you say yes, I want you to touch on all those. I want you to tell me why. If you say yes, I want you to mention that all of those are met. You have a small p-value, you have a high R-square value, your standard deviation's low, your prediction intervals are narrow. This is the best thing since sliced bread. So that's how we check it in practice. All right, let me end with this. Our next step, we're going to include other model terms in the regression model to better estimate Y. We're getting there, folks. We've looked at simple linear regression. We've now added the multiple regression and say, hey, let's stretch a little bit. We've got some more stretching to do. Quadratic terms, I've talked about them. All right, maybe it's not a linear relationship. Maybe it's a curvilinear. We saw some diamond prices earlier that just definitely look like some curves. What the heck is interaction? Probably the toughest of these 3. And then this particular example I did with the traffic data had a qualitative variable, but I'll take a closer look at it so you get a better taste of what those qualitative variables do. So that's our next step. Come on back and take a look at that, and then we start going crazy. We start creating model terms, x1, x2. This is called an interaction term, where you're multiplying terms together. x1 squared, that's a quadratic, and this guy, that's just nuts. It's a quadratic, it's an interaction term. There's a quantitative component, because x1 is a quantitative variable. There's a qualitative component. That thing's just crazy. And we'll talk about why we need those things and how we use those in our multiple regression work. So model terms, that's where you head to next. Good luck.